So all 5 of them are tetrahedral. Do they all have polar bonds? Are these polar bonds? Carbon and hydrogen bonds. They will be polar. Carbon-chlorine bonds, they're polar. But are they more or less polar than carbon-hydrogen bonds? Will they be more polar or less polar? A chlorine carbon or a hydrogen carbon? Which one will be more polar, the bonds? So chlorine has a higher electronegativity than carbon, so that would be a polar bond with a partial negative on this side and partial positive on this side. So carbon-hydrogen, which one's got a higher electronegativity? Carbon. So that would produce a partial positive, partial negative. So you've got a partial negative here. So you've got partial positive, partial positive, partial positive, partial negative. Is that a polar or non-polar molecule? It's got positives on one side, negatives on the other side. So it'll be polar. This one will have negatives, positives, so it'll be polar. This one's got a positive, negative, so it'll be polar. This one's got negative, 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 so that would be non-polar. So that's negatives. This one's positives, but they're both non-polar. Okay? So those 3 are not symmetrical. So chloromethane. So looking at our dipoles, so that polar bond is positive, negative. We've got a dipole in that direction, dipole in that direction, dipole in that direction, net partial negative, partial positive, dipole in that direction. So they're all pointing to give a net dipole with positive on this end and negative on this end. Okay? So remember that just because they've got polar bonds does not mean that it's going to be a polar molecule. You've got to look at the distribution of those bonds. For the molecule to be polar, you need to have a polar bond as well as an asymmetry in the molecule shape. So there are those 2 things that we need to consider for molecule polarity. So if we look at ammonia, so ammonia is this shape, but instead of having that atom there, it's got a pair of unbonded electrons. So in this case, partial negative here, partial positive, partial positive, partial positive. You've got positive on one side, negative on the other side. Clearly it's a polar molecule. So we know that the ammonia is the pyramidal shape. So it's a pyramidal shaped molecule. Slightly negative at the top because of the polar bond. Because this has got a higher electronegativity than the hydrogens. These are positive because the electrons are drawn that way. It's got polar bonds. It's asymmetrical, so it's a polar molecule. So you can see the logic process that we're going through there. First of all, what's the shape of the molecule? What's the polarity of the bonds? What's the distribution of the bonds within the molecule to work out whether or not it's polar or non-polar? So a few definitions. A dipole. So a dipole is a permanent build-up of negative charge on one end of the molecule. That's important to remember. Positive one end, negative the other end, across a covalent bond. Yep.
So isotopes have different electronegativities, and if so, would covalent bonds of like O2 have?
So electronegativity is determined by the core charge, which is the same for an isotope. because the only thing that changes in an isotope is the number of neutrons
Yep.
and the size or the radius of the atom.
Yeah.
So that, again, is not affected by the number of neutrons. So isotopes have very similar chemical properties. Yeah. So a polar molecule is a separation of charge from one region to the other, or so from one side to the other. Polar molecule, polar bond. Polar covalent bond is a covalent bond where the charge has been separated, which we discussed yesterday. All right, so let's have a look at these. Which ones of these, if any, would be polar? So what I want you to do is I want you to draw those, and I want you to draw in the partial negatives and positives of the bonds and work out where the charge is distributed and hence whether or not they're polar or non-polar.